So in this video, we're going to look at one specific example of applying Maxwell relations to find thermodynamic functions that we can't measure directly by knowing pressure, volume, and temperature data. So we're going to look at the Maxwell relation that we get from the Helmholtz energy. dp dt at constant v is equal to ds dv at constant t. So we'll start with this partial derivative on the right-hand side of the equation. If we consider ds dv at constant t, if we wanted to find a change in entropy for a system, we have this currently as a derivative. If we want to do the opposite of derivative, we need to do an integral. Right? So if we integrate, since this is dv on the bottom, we're going to integrate over volume, going from volume 1 to volume 2. This would give us a value for delta S, going from v1 to v2. Okay, but probably we don't know how entropy changes with volume at constant temperature, and this is where the value of these partial derivatives, this Maxwell relations, come in, is we can use a substitution here. We know this partial derivative is equivalent to this other partial derivative that has things that we can measure, but it'll still be equal to the change in entropy because these partial derivatives are equal. And so we can keep the same, everything else the same, and just make a substitution. So we still integrate from volume 1 to volume 2. Now we change the partial derivative that's in here and dv, and it's still equal to delta S, going from volume 1 to volume 2. What's the change in entropy? And now we have something where if we know pressure, temperature, volume data for a system, we can find the change in entropy for that system. And so the way this would often work is that we could do this for the ideal gas law. We'll look at that just to show that this works and we get an entropy change that's equivalent to something we've already calculated. But this would also work if we wanted to, say, use the van der Waals equation or the Redlich-Kwong equation. Right? We can find a derivative from that gives us an expression we can put into this integral. We integrate and we can find an entropy change even if it's not an ideal gas. That's where the real power of this comes in, is that we're not limited to thinking about just ideal gas behavior. Because nothing in this derivation here of Maxwell relations relied on the fact that we had an ideal gas. So let's just prove that this works with the ideal gas law, though, just to keep it simple. Right, so if we have the ideal gas law, right, PV equals nRT, we can go ahead and rewrite this. We want to find dp dt at constant v. So, okay, what's P? P is equal to nRT over v. And now let's take the partial derivative of that with respect to temperature, right? So we need to go partial derivative with respect to temperature, keeping volume constant. All right, so dp dt at constant v of this expression, so v is constant, t, we'll get nr over v for the ideal gas law. Now, if we did this for the van der Waals equation, we get a more complicated expression, but we would still get something we could integrate, or Redlich-Kwong, or anything else. Or if this would apply even to non-gaseous things, we could also do this. Okay, but we can go ahead and substitute this expression into our integral here and make sure we get something that matches what we've already found before for ideal gases. Integrate from v1 to v2, nr over v dv, and we can see we're going to get nr log v2 over v1 is equal to delta S. Okay, and so what we were considering, just coming back up to our original integral here, we were considering a volume change. And one thing we have to look at is that T is constant. So this is an isothermal process. So this should match what we got for volume change for an isothermal process, isothermal compression or expansion. And this is, in fact, this should look familiar. This is the expression we derived for an isothermal expansion, what the change in entropy is. And so this is just to show that this works. But unlike the way we derived it earlier, where we had to assume ideal gas behavior, here we can use any equation of state. It doesn't have to be the ideal gas law. It could be a van der Waals equation or something else. And we could still find an expression for the change in entropy for an isothermal compression or expansion. So this just gives us a more general toolbox to use.